Welcome to the second lecture on the topic of special relativity. So we're going to be picking up from where we left off last week. Just before I start, a quick word on maths and formalism, because a few people have asked me about this. This is something I've already said to my own seminar group, but it's worth saying to everybody. When it comes to especially the topics of special relativity and general relativity, obviously you'll come across some math, some formalism in textbooks, also to some degree in the lectures when we're talking about these topics. Now, for some of you, the maths might be reasonably straightforward. It depends on your background. For some of you, it might not be. For those of you for whom it isn't straightforward, don't be put off. So remember, this is a philosophy module. So basically, what we're really looking for is the kind of take-home conceptual messages. So as long as you're clear on those, then you don't need to be able to reproduce any of the maths. So we look at things like the interval measure in space-time, in Minkowski space-time. So it's not so important that you remember the formalism for the measure or that you be able to use it to prove things. Rather, the sort of types of important philosophical take-homes are that, for instance, the interval measure gives us something absolute. So this space-time interval doesn't vary across reference frames. It's something absolute, and so arguably an absolute feature of the space-time, which may be relevant to the absolutism versus relationalism debate. Other sorts of important take-homes are the fact that there's no notion of absolute rest in Minkowski space-time. And also no notion of absolute velocity, right? So we can distinguish velocities from accelerations in terms of what the world lines look like, whether they're straight or curved. But we can only speak about degree of velocity in relative terms. So those sorts of well-established facts about special relativity are the sorts of facts that are important to have in mind if you're writing about this in an essay. It's not very important that you should be able to produce the sort of mathematical demonstration that these facts obtain. They can be taken for granted. So that's not to say if you want to include formalism, that's fine. But the primary point of the module and of the essays is going to be a kind of conceptual philosophical one. Okay, so with that in mind, I'm going to proceed. So again, there will be formalism this week, and follow it as best you can, but also pay attention to the sort of philosophical messages that come out of this formalism. Okay, so I'll switch to the handout now. And so, same handout as last week. So this is covering 2 weeks worth of material because special relativity is a big topic. So we got all the way to section 7. Well, we finished section 6, where we introduced the Minkowski space-time diagrams with the double light cone structure. And so we're ready to start section 7. So if you've got the handout in front of you, then skip to section 7. So let me just full screen this. So we're starting with some more interesting features of Minkowski space-time and a kind of surprising consequence that we get in virtue of the structure of Minkowski space-time, and in particular the interval measure, which is this space-time distance measure appropriate to Minkowski space-time. And this surprising phenomenon is the twins paradox, which we'll come on to in a moment. But first, let's introduce the clock hypothesis. So the clock hypothesis in special relativity is the hypothesis that the amount of time that an accurate clock shows to have elapsed between two events, or if you like, two space-time points, is proportional to the interval in the sense that we define, the mathematical sense, the distance measure. So it's proportional to this interval along the clock's trajectory between those 2 points. That is to say, accurate clocks measure their own trajectory or interval through space-time. So we'll come back to that. It's going to be relevant to the twins paradox because the idea is that if you have two twins, each on their own trajectory through space-time, and that each has an accurate clock, then basically their own clock is going to measure the interval of space-time that they've traversed, right? Which and these intervals might be different, even though they start at the same space-time point and end at the same space-time point. They might nevertheless traverse different intervals, and so their clock readings will be different. So that's going to be important in the twins paradox. So, all right. So suppose this is the interesting and I guess some would say paradoxical. It's not really a sort of logical paradox in any sense. It's kind of something maybe surprising, but there's no logical contradiction in it. So special relativity implies that, so we've got two twins, and they've got clocks, maybe each is issued with some sort of accurate clock, an atomic clock, say, prior to their journey. And we're going to suppose that twin B is kind of the boring one. Twin B is just going to move inertially through space-time at a constant velocity. Twin A, on the other hand, is they're going to start together, right? So twin A and twin B start off together. Maybe they start on their spaceship, traversing an inertial trajectory through space-time. But then twin A is going to get into the little pod in the spaceship, which, maybe it's like a landing vehicle or something like that. It is going to accelerate away from twin B, who remains in the main spaceship. It's going to go some distance and then accelerate back to twin B. At which point, twin A's pod's going to join back with the main spaceship, and they're both going to carry on moving inertially from that point. Now, so this is just the sort of summary. We'll go into more detail about what's going on in a moment. But the sort of surprising consequence is that at the end of this episode, so once twin A and twin B are reunited, then twin B, the one that remains in inertial motion all along, her clock is going to display a later time than twin A's clock, twin A being the one that accelerated away from twin B and then back. And also twin B will be physiologically older than twin A. So their sort of biological age, if you like, will be a little bit older than the one that accelerated away. And this is known as the twin paradox. So let's go in a bit more detail about what's going on here. So I said something about Lorentz coordinate systems last week. So a sort of Lorentz coordinate system is a kind of coordinate system that's appropriate to Minkowski's space-time, just as a Cartesian coordinate system is a coordinate system familiar or sort of appropriate to Euclidean space. We'll say a little bit more about Lorentz coordinate systems later in this lecture. We said a little bit last lecture as well. So suppose we're going to choose a Lorentz coordinate system. We remember there's a certain amount of arbitrariness to that. So your choice of you're basically free to select the origin point and also the orientation of the axes as long as they're perpendicular to one another. There are some constraints, I should say, on the t-axis, right? So the t-axis has to lie within the future light cone, or I should say the light cones, the double light cones of the origin point. But there's certainly a certain amount of arbitrariness in selection of a Lorentz coordinate system, so we can just select one that suits us for whatever purpose we're putting it to. So just for simplicity, we're going to select one. So we're going to suppose that basically twin A and twin B are moving inertially, and it's at space-time point P that twin A leaves twin B to accelerate off into space. So for simplicity, we're going to choose a Lorentz coordinate system that has as its t-axis the world line traversed by twin B, right? So twin B's world line is going to correspond. So that's an inertial world line, a straight line, is going to correspond to the t-axis of our chosen Lorentz coordinate system, and that's just going to make the calculations a little bit simpler. Okay, so we've got this point P where they diverge, twin A and twin B do, that serves as the origin point of our axis. The t-axis is going to correspond to twin B's world line. And indeed, up until the origin point, it's going to be the case that twin A and twin B are traversing the same world line. So they're both aboard the same inertially moving spaceship, but it's at the origin point P that twin A diverges, twin A accelerates away, i.e. moves in a different direction from twin B until twin A gets to point Q, at which point twin A is going to turn around and come back to twin B, who continues to move along this inertial path given by the t-axis. And their reunion point is the point R in the diagram, so in figure 3. Okay, so we've simplified by just the calculations by letting the divergence point correspond to the origin of our chosen Lorentz coordinate system. Another way in which we've made things simple is by choosing a Lorentz coordinate system where the t-axis corresponds to twin B's world line. And we're going to make a third simplifying assumption that, again, just simplifies the calculations a little bit, which is we're going to suppose that relative to our chosen Lorentz coordinate system, twin A moves away from twin B only along the x-axis. So, of course, there are 3 spatial dimensions defined by the x, y, and z axes. We're going to suppose that in this Lorentz coordinate system, twin A moves away from twin B only via a movement along the x-axis. Okay. So, all right. So yeah, in the diagram, twin B's world line represented by the blue t-axis the bit of twin A's world line that diverges from twin B's world line is represented by the green lines, firstly from P to Q and then from Q to R. Okay, so because we've chosen a coordinate system according to which point P coincides with the origin, so the coordinate points of that are just 0, 0, 0, 0. So 4 coordinates. That's just the coordinates of the origin. And then point R only differs from point P, we can see from the diagram, along the t-axis, right? So it doesn't differ, if you like, spatially from point P, only diverges along the t-axis. So let's suppose that we haven't stipulated a unit of time. It could be hours or days or something like that. But whatever unit we stipulate, let's just suppose that the R differs from P by 1,000 units, whether that be 1,000 hours or 1,000 days, or whatever. So the coordinates for point R are 1,000, so the t value is given first, and then the x, y, z coordinates, which is 0, 0, 0, because point R lies on the t-axis. So that the t-axis at every point has x, y, and z coordinates of 0. Okay. And so finally, we'll suppose that Q is half the distance between P and R along the t-axis. So the first coordinate, the t coordinate of Q is 500. We stipulated that Q doesn't differ from P along the y and z axes, so the y and z coordinates are 0, and we'll just stipulate that the x difference of Q from P, in other words the origin point, is 300 units. So that might be 300 light hours or something like that. So that gives us our Q coordinates, which are 500, 300, 0, 0. Okay. So what we want to do now, and this is going to show how the twin paradox arises, is calculate the space-time interval traversed by each of the twins between their separation point at P and their reunion point at R. So, as we said, each of their clocks is going to measure the interval they've traversed, right? So we want to compare the interval traversed by twin B, the one that goes along the t-axis, to the interval traversed by twin A, which consists of these two green lines. Okay, so so actually I'll go to the calculation for the interval traversed by twin B first. So that's really quite a simple calculation, because the point P differs obviously from point R along the t-axis, and twin B remains on the t-axis, so just traverses that world line. So actually, we basically only need to calculate the interval corresponding to the segment of the t-axis between points P and Q. So Twin B, if you like, doesn't do any spatial maneuvering, but just sits on that t-axis. So we only have a change in a single coordinate, namely the t-coordinate, to take into account. So this is given in equation 8, right? So so basically, if you recall the interval measure tells us that the interval between two space-time points corresponds to the square root of the squared difference in the t coordinates with the summed squared distances upon the x, y, and z coordinates subtracted from that. But in this case, we've got a significant simplification because b just doesn't go anywhere on the x, y, and z coordinates. So we'd be essentially taking the squared difference in the t coordinates and just subtracting 0. So we can ignore that. We don't need to. Subtracting 0 obviously just yields the same thing again, the difference in the t coordinates. So we have a fairly straightforward equation for the interval traversed by twin B, which is just the square root of the squared difference between the 2 points on the t-axis. So actually there's a typo here, so it should be r rather than p. So this is the function that returns the t coordinate of point r, and here we've got q as a function, so it returns the t coordinate of point q. Now, again, we've simplified by supposing that point q corresponds to the origin, so its t coordinate is just going to be 0. So the t coordinate of q is just 0, right? So that's going to give us 0 there. Now, the t coordinate of r we've supposed is 1,000, right? So we've supposed that r differs from p by 1,000 temporal units, so maybe hours or days. Okay, so then our interval measure is just the square root of 1,000 minus 0 squared. In other words, that simplifies to the square root of 1,000 squared, which is the square root of 1,000,000, which is just equal to 1,000, right? So we get that the interval between p and r traversed by this straight line along the t-axis is just 1,000 units, right? Which is what we'd expect. Okay. Now, the situation with twin A differs, interestingly, from this. So how do we, basically, as I said, in order to figure out the interval traversed by twin B, we're just looking for the length of that blue line, PR. In order to figure out the interval traversed by twin A, what we need to do is we need to sum the interval of the line PQ with the interval measure of the line QR, right? And that will give us the total interval traversed by twin A during this episode. Okay. So, again, because we've simplified, we can ignore the y and z axes, right? So we've simplified by supposing that twin A just doesn't move away from twin B by any distance along the y and z axes. It's purely with respect to the x-axis. So all we have to worry about when determining the interval that twin A has travelled is the distance they've travelled along the t-axis and the distance they've travelled along the x-axis. So that makes our interval equation simpler, as given in equation 6. So firstly, so 6 is the calculation of the interval between the origin point P and the point Q, right? So we're going to figure that out first, and then we're going to figure out the interval between P and R. We're going to add the two together, and that's going to give us the total interval traversed by twin A. Okay, so what we do according to the interval measure in figuring out the interval between P and Q is take the square of their distance along the t-axis from one another, subtract the square of the distance along the x-axis that they have to one another, and then take the square root of the whole thing. Now, again, our simplifying assumption comes in handy because we've supposed that P has the coordinate 0, 0, 0, 0. That is to say, it's just the origin point. So we know, of course, that the t coordinate of Q is going to be 0, and so we get to plug that into our equation. And likewise, the x coordinate of Q is going to be 0, so we get to plug that in too. Now, we can suppose, so then we've got to make some suppositions about where Q lies on the t-axis and the x-axis. So we've supposed that Q is half the t distance from P that R is. So Q has t coordinates of 500. Remember, P's t coordinates are 0 and R's t coordinates are 1,000. So obviously half the distance is going to be 500. And we can suppose, just for the sake of argument, that the x-coordinate of Q is 300. Okay, so that we just plug in those values, 500 for the t-coordinate of P, 300 for the x-coordinate of P. And then we just do the calculation, right? So obviously the 0 is not doing anything, so this simplifies to the square root of 500 squared minus 300 squared, and then you just do the maths, and the upshot is that the interval length of the line PQ is 400. Okay. The length of the line QR is calculated similarly, so we're going to look at the difference between Q and R along the t-axis. So again, that's 500 because if you recall, R has a t-coordinate of 1,000 and Q has a t-coordinate of half that of 500. So the difference between 1,000 and 500 is obviously 500. So the first expression here is going to be 500 squared. And then we look at the x difference between Q and R. Well, I mean, in a sense, this is quite simple because we've supposed that R has the x value of 0, and Q we've supposed has the x value of 300. So in order to determine the difference in x value of R and Q, we just subtract the x value of Q from the x value of R. So the x value of R is 0. The x value of Q is 300. And so the result is minus 300, which we've got to square, right? So that actually the fact that it's negative, if you like, r's x value is less than q's x value. That the fact that it's negative just disappears because of the operation of squaring, as we'd want it to do. And so again, by calculation, and it should be fairly obvious from the symmetry of the case, we get the result that the line QR has, again, 400 interval measure. So in order to figure out, obviously, the total interval traversed by twin A, we sum the interval of the line PQ and the interval of the line QR. So we add 400 to 400, and the result is 800. Okay, so that's just a lot of calculation. But what's interesting is when we compare our calculation for the interval traversed by twin A to that of the interval traversed by twin B. So twin A has gone a total of 800 units, whereas twin B, the one who remains in inertial motion, has traversed a total of 1,000 interval units. So obviously we can see that the interval traversed by twin A, the one who accelerated, is lower than the interval traversed by twin B, the one who remained in inertial motion. It's 80%. So twin A has travelled 80% of the interval traversed by twin B. Now, one thing that's sort of interesting about this is that it kind of exhibits how unlike Euclidean space Minkowski space-time really is, right? Because in Euclidean space, we have the so-called triangle inequality, right? Which says that the length, if we take the length of a single side of a triangle, that's going to be less than the sum of the lengths of the other two sides of the triangle. So that's fairly intuitive, and very intuitive when we're familiar with working with Euclidean geometry. However, the interval measure violates this, right? Because we've measured, so the PQR forms a triangle, right? Now, we've measured the interval PR, which is the line traversed by twin B, and we've also summed the measure of the interval PQ and the interval QR, and what we found is actually the interval PR is actually greater than the sum of the interval PQ and the interval QR, and not less, right? So we found kind of the opposite of what we'd expect to find in Euclidean geometry. We found that by the interval measure, the one side of the triangle is longer than the sum of the other two sides. So this is, something interesting about Minkowski space-time. And so it also highlights the limitation of Minkowski space-time diagrams because, this is a Minkowski space-time diagram, figure 3. And yet you sort of look at it and you think, well, just looking at it, you can tell that actually, as it's drawn on the paper, the sum of PQ and QR is longer, not shorter, than the line PR. But that's an artifact of representing or trying to represent Minkowski space-time on a piece of paper, or if you like, on a computer screen. What we're doing is we're trying to represent something that's non-Euclidean on a surface that actually approximates a two-dimensional Euclidean plane. So obviously there are going to be distortions, and this is one distortion: the fact that when we just look at it, when we just look at our diagram, the sum of the lengths of the green line look longer than the length of the blue line segment from P to R. But that's pure artifact, and according to the interval measure of Minkowski spacetime, actually the line PR is the longer one. Okay. So now, I suppose you might say, well, have we actually shown anything interesting? You might think, okay, well, yeah, sure, you can come up with some measure or other that's going to make PR longer than the sum of PQ and QR, right? If you're just allowed to choose any measure arbitrarily or invent one, then you can get that result. But why should we care about that? Why should we think of that measure as in any way corresponding to a distance measure, a measure of distance, and a sort of measure of interest? And basically the reason is that there's sort of empirical consequences that can be observed that give some vindication to the interval measure. So one of them is one that I alluded to earlier, that if we've issued both of the twins with reliable clocks at the start of the episode, remember, according to the clock hypothesis, reliable clocks measure the lengths of the trajectories of A and B. So actually what we find is that, as the interval measure would predict, the time elapsed on twin A's clock, the one, remember, who accelerates, is only 80% of the time elapsed according to twin B's clock. So this is an empirically provable consequence that holds in our world, that if you have a clock that's accelerated away from an inertially moving clock and then returns to that inertially moving clock, the clock that has been accelerated will show less time to have elapsed than the clock that's remained in inertial motion. And likewise, it's not just clocks, but biologically, twin A, the one who accelerated, will physiologically have aged less than B during the episode. So biologically, twin A will have aged to only 80% of the degree to which twin B has aged throughout the episode. So, obviously, if this episode's quite a long one, right? So maybe for twin B, or twin B maybe measures 50 years to have elapsed. Twin A is only going to measure 80% of that to have elapsed, so 40 years. And so while twin A will have aged 50 years, twin B will have only aged 40 years during the episode. And so that's going to be a detectable difference. Okay, so interesting. So this sort of this violation, this sort of very strong and interesting violation of Euclidean measures of distance that we've pointed to in Minkowski spacetime, showing in a sort of fairly dramatic fashion that Minkowski spacetime is non-Euclidean, and so is unlike the sort of space that was supposed by people like Newton and Leibniz, and even Galileo. Okay, so and yeah, I mean, interesting empirical consequences of that. So we can tell empirically, in other words, that our space is a non-Euclidean space, or our space-time is a non-Euclidean space-time, because of these empirical consequences to do with clocks and aging and so on. Okay. All right. So having shown that, so we're going to change topics a little bit, or at least revert to an earlier topic, which was the topic concerning the assignment of Lorentz coordinates. So for the purposes of that illustration of the twin paradox, I chose a Lorentz coordinate system that made the maths a bit simpler than it would have otherwise be. I mean, it doesn't distort in any way. You get the same results if you chose a different Lorentz coordinate system, because space-time interval is something that's invariant across Lorentz coordinate systems. So we get the same results. It's just calculating the results would be just mathematically a little bit more difficult. Okay, so but let's think a bit more about Lorentz coordinate systems. So one way of thinking about them, sort of influenced by Einstein, is to suppose that we have this is sort of hypothetical, obviously. We have a limitless supply of clocks that are in perfect working order. Perhaps they have different scales, so one might display minutes, another might display seconds, another might display fractions of seconds, and so on. Now, we'll suppose that each of these clocks measures time from some zero moment. So I guess they work in a way like stopwatches. Show the time that's elapsed from some zero moment, and which moment counts as zero might differ across the clocks, and in all cases it's just arbitrary. It's not like they've been calibrated to correspond to some interesting physical event. Like, it's not like the Big Bang was the zero moment for all of them. Okay, now suppose that all of these clocks are moving inertially. They're traversing straight line trajectories through space-time, and correspondingly they're not subject to forces. Now let's choose one of these clocks and call it Ben, and this is going to serve as our master clock. So basically the idea is, of course, according to the clock hypothesis, reliable clocks measure the space-time interval along their trajectory where they're moving inertially. So every event on the world line, the trajectory of Ben, is assigned a t-coordinate by Ben, right? So the t-coordinates of every event on the world line just corresponds to whatever time Ben is reading at that point of that event. Now, other clocks, we can define a notion of co-movement. So, for instance, another clock, we'll call it Chloe, is said to be co-moving with Ben if and only if Chloe is also on an inertial trajectory and Ben and Chloe are neither approaching nor receding from one another. In other words, their world lines are parallel. Now, basically, you can check whether two clocks are co-moving via empirical experiments. So suppose you've got an observer who's situated with Ben moving. So maybe Ben is this observer's wristwatch, and the observer's moving inertially. Then this observer can identify that Chloe is a co-moving clock by sending out light rays from Ben and seeing how long it takes for the light rays to be reflected by Chloe and to return to Ben. So in our diagram, so figure 4, the blue lines are going to represent light rays. Now, if Chloe is co-moving with Ben, then of course each light ray emitted from Ben and reflected off Chloe is going to take the same amount of time to return to Ben. Okay, so this is illustrated. So if you like, the horizontal lines on Ben could correspond to unit of time measurements. So maybe the first horizontal line corresponds to a reading of 1 o'clock or 1 unit of time. According to Ben, the observer emits a light ray at 1. It bounces off Chloe, reflects back to Ben, and when it arrives at Ben, the reading on Ben is 4. So left at 1, returned at 4. So we've got a 3-unit interval that it took for the round trip to occur. And so maybe the observer sends another light beam to Chloe at 5 when Ben's reading 5. And it bounces off Chloe and it gets back to Ben when Ben reads 8. So again, the second light beam has taken 3 units of time, according to Ben, to make the round trip. And that's just the same as the first beam of lights took, right? So both took 3 units of time to make the round trip, which indicates that Chloe is neither getting closer to Ben over time nor receding from Ben. In other words, that they're co-moving. Now, contrast this to the case of Ben and Dan. So Dan is a clock that's not co-moving with Ben. And this is illustrated by the fact that it takes increasingly long. So Dan actually is receding from Ben in this instance. And so light beams reflected off Dan, emitted by Ben, and reflected off Dan take increasingly long time to complete their round trip journeys. So in the figure, the first beam takes 3 hours to make its return journey. The second beam takes more than 4 hours to make its return journey. I'm supposing the unit of measurement is an hour, but it doesn't have to be. So 3 units, and then it takes more than 4 units. And so that suggests that Dan's receding from Ben. Obviously, if the second measurement took less units than the first one, that would suggest that Dan's approaching Ben. But in either case, not co-moving. Okay, so co-moving clocks are interesting. So they can be calibrated or synchronized, if you like, by well, actually, we'll get synchronization in a minute. Calibration and synchronization, subtly different, right? So calibration, we have Ben send out a light signal every 4 hours, and we adjust the co-moving clock. So we adjust Chloe, for instance, so that Chloe also shows that 4 hours have elapsed between the receipt of each light signal, right? So, or should I say 3? Yeah, so it's 3 hours. Sorry, no, it's 4. 4 was right. So, because what's going on is Ben's emitting a light signal every 4 hours, right? So the first one is emitted at 1. it's received back at 3, but then there's an hour wait before the second one is emitted. So the total time that's elapsed between the sending of the light signals is 4 hours. So we calibrate Chloe by likewise adjusting Chloe's timekeeping so that Chloe also shows that 4 hours or whatever the unit is of measurement have elapsed between the receipt of the light signals. And then synchronization would be essentially ensuring that the 0 point of Ben and Chloe correspond, right? So the way we'd do this is by, well, if Ben reads 1 here at the sort of bottom line where the first light beam's emitted, and reads 4 where the first light beam is received, then what we'd want to do is to set Chloe so that Chloe's reading is 2:30 at the time that the first light beam is received, right? So that will give us our synchronization between the clocks. Now, okay, right. Okay, so sorry, I'm just looking at what I've written and checking I haven't missed anything. Yeah, okay. So sometimes this approach as an application of a synchronization convention, right? Because there's kind of an assumption in special relativity that the light is moving the same speed in both directions, right? So it's assumed that. So the reason we set Chloe so that Chloe's reading is 2:30 if the beam leaves Ben at 1 and arrives back at Ben at 4. So we sort of split the difference. We take the midpoint and assume it's a sort of midpoint time at which the light arrives at Chloe is based on this assumption that the light travels the same speed in both directions. Now that's an assumption and or a convention, and hence this way of doing things is known as the Synchronization Convention. Right, good. So it turns out that you don't have to make that assumption in special relativity. You can make alternative assumptions, but this is a straightforward one to make. But it's sort of interesting that it's not neither the theory nor the empirical data determine that you have to make this. This is definitely true. Okay, so suppose that we've shown how we can determine that Chloe is a co-moving clock, and we can calibrate and synchronize Ben and Chloe. And in general, you could do that with any co-moving clock. So we might do this with a whole bunch of clocks. And if we had enough clocks, then this would allow us to determine Lorentz coordinates for events throughout all of space and time. So sometimes we talk about a complete set of clocks that's co-moving with Ben, So a complete set of clocks co-moving with Ben would be one that, I mean, again, this is rather fanciful stuff, but it's supposed to sort of show, how Lorentz coordinates could practically be assigned to every point in space time, even if actually it's our universe doesn't allow for this because we don't have enough clocks. But if we did have a complete set of clocks co-moving with Ben that filled the whole of space time and calibrated them and synchronized them according to the principles that we've described above, then this would allow us to assign t coordinates to each space-time point. We'd just read them off, read the t coordinates off the clock that went through the relevant point. Okay. Now, so things are a bit different if we choose Dan as our master clock rather than Ben. So I've introduced another clock, Al, that's co-moving with Dan. But Al and Dan aren't co-moving with Ben and Chloe. They're receding from Ben and Chloe. Now, because Al and Dan are co-moving, we can synchronize and calibrate them as we did with Ben and Chloe. Now, the obviously Al and Dan are tilted with respect to Ben and Chloe, and so they're going to yield a different Lorentz coordinate system with a t-axis that's tilted relative to the t-axis defined by Ben. Okay, so right. Okay. So now, so you might think that maybe there's something special about Ben and Chloe that might make us want to say, look, they define something like absolute rest or a privileged Lorentz coordinate system, somehow superior to that defined by Al and Dan. And you might say, well, the reason is that if you look at the light signal that travels from Ben to Chloe and back, well, the blue lines representing the trajectory traversed by the light are of equal length, right? So I said, by the way, that the idea that the speed is the same in each direction is a convention. You might think, well, actually, we can't empirically determine that they're of equal length, but nevertheless, you might think, well, there's got to be some fact to the matter. So if the ones traveling from Ben to Chloe and back are indeed of equal length, then maybe that privileges them as a reference frame. Whereas it looks like, if we send a light signal from Dan to Al, which gets reflected back off Al back to Dan, then it looks like the outward signal, just because the tilt is traverses a longer distance than does the return signal from Al to Dan. But actually, this is a pure artifact of the diagram. It's a pure artifact again of attempting to represent Minkowski space-time using a diagram on a surface that approximates to a two-dimensional Euclidean plane. So there's no actual distinction in Minkowski space-time between the tilted, the tilted and the non-tilted, and in particular, there's no sort of physical reason to think that the line traversed by light between Al and Dan is going to be longer in one direction than in the other direction. We have no more reason to suppose that than we do when it comes to the relationship between Ben and Chloe. Okay. All right, so we've thought about how we assign t coordinates in terms of co-moving clocks, but we can also assign x, y, z coordinates relative to a master clock. So basically, the x, y, and z coordinates. So we've got the world line of the master clock that defines the t-axis. The x, y, and z axes are just going to be basically all four axes have to be orthogonal to one another. So that's the constraint we must meet. So we just choose three lines that are orthogonal to the master clock's world line and each other. And then we can assign coordinates, right, according to these axes, right? So once we've chosen these three orthogonal lines, we can send out light signals along them, right? So suppose we first take the line that we've chosen as our x-axis, and we send out a light signal, then that's going to be received by some but not all of the co-moving clocks, right? It's going to be received by the ones that lie along the x-axis that we've chosen, but not those that don't lie on that x-axis. And then we can send a light signal out in the opposite direction, and that'll reach the clocks lying upon the negative x-axis, and basically we can assign coordinates, x coordinates, to clocks that lie along the x-axis on the basis of the time it takes for light to be reflected back off them and to return to the master clock. So if it takes, for instance, 2 seconds, according to Ben, for the return journey of light to, say, Chloe, a co-moving clock, we'll suppose that Chloe lies on the x-axis, then the coordinates, the x-coordinate of Chloe would be 1 light second away from Ben, because the return journey takes 2 light seconds, right? So we suppose that Chloe just lies half of that distance along the x-axis. Okay. And we do this exact same thing for the assigning coordinates along the y and the z axes. And then once we've got that, we can assign coordinates to other clocks by an analogous procedure. Okay. Right, okay, so, there's a certain, as I said, sort of arbitrariness to our choice of Lorentz coordinate system. So we sort of define a Lorentz coordinate system with respect to an arbitrary origin or 0 point, and an arbitrary world line. So we just choose a master clock, say, and a sort of arbitrary choice of orthogonal x, y, and z axes. So there's a lot of sort of wiggle room in providing a Lorentz coordinate system. There's not like one objectively special one as well, so there's nothing to distinguish between say the Lorentz coordinate system that we might define starting with Ben, or say a Lorentz coordinate system that we might define starting with Dan as our master clock. So yeah, but that's again just kind of as we'd expect with a coordinate system. Very much the same thing is true in Euclidean space when it comes to Cartesian coordinate systems. There's there's flexibility in what Cartesian coordinate system we choose. We choose an arbitrary origin point and we choose the angles of our axes. So as long as they're orthogonal to one another, then we have a suitable Cartesian coordinate system. So there's a certain amount of this that's just arbitrary. But I suppose sort of one thing that's kind of interesting and is that there are certain quantities that don't vary across choices of coordinate system. And you might think of those as the physically real quantities. They're not just artifacts of how we've chosen our coordinate system. So within with a Cartesian coordinate system, length is invariant. So the length between 2 points in space, in a Euclidean space, isn't affected by the choice of Cartesian coordinate system. It might be that our calculation of the value is different depending upon the way that we've assigned Cartesian coordinates, but the value we get for length isn't going to differ. And likewise for Lorentz coordinate systems, when it comes to the interval measure, right? So again, the calculation might wind up being a bit different or looking a bit different depending upon our choice of Lorentz coordinate system. But the value for the interval we get is invariant. It doesn't vary across Lorentz coordinate systems, and hence this looks like something physically real. Another interesting thing that, and this has already been anticipated, that doesn't vary across Lorentz coordinate systems is the behavior of light, right? So the behavior of light it is insensitive to the choice of Lorentz coordinate system. For instance, the behavior of light, what we observe if we choose Ben as our master clock, is going to be exactly the same sort of thing that we observe if we choose Dan as our master clock. Even though Dan and Ben are tilted with respect to one another, this isn't going to make any difference to what we observe when we send light beams out from either of them. So again, they're going to identify co-moving clocks in exactly the same way. Okay. So the final phenomenon that I want to come on to before ending this lecture is the phenomenon of length contraction. Now that we've sort of got the interval measure in play, then so length, right? So I said that length or distance in Euclidean space is invariant. So your choice of Cartesian coordinates doesn't make a difference to your measurement of length in a Euclidean space. When it comes to choices of Lorentz coordinates in a Minkowski space-time, well, the choice doesn't make a difference to the interval measure, but it does make a difference to length. So different distance along the x, y, and z axes. So that's not an invariant quantity in Minkowski spacetime, whereas interval is. So we'll see that. Well, on the handout I've said, suppose that in the Lorentz coordinate system defined by Ben, Chloe is 90 light minutes away. I've changed that. I said something different. I said 2 light minutes away, but that was just for an illustration. We'll suppose now that Chloe's 90 minutes away from Ben. Otherwise, you could choose a different co-moving clock that is 90 minutes away from Ben. And likewise, let's suppose that in the coordinate system defined by Dan, Al is 90 light minutes away from Dan. Okay. So just because Al is 90 light minutes, so light minutes being a distance measure, the amount of distance traveled by light in a minute, light in a vacuum, that is. Just because Al is measured to be 90 light minutes away from Dan by Dan, it doesn't follow that Al will be measured to be 90 light minutes away from Dan according to Ben, right? And in fact, this won't be the case. Dan, the distance, the length between Dan and Al is going to depend upon the perspective provided by our Lorentz coordinate system. And this is a phenomenon known as length contraction. So we saw length contraction in operation in the Einstein train experiment from last week. But we can now sort of provide calculations of the degree of length contraction that we can expect to observe across Lorentz coordinate systems. So just to illustrate, we can suppose that we've got this Lorentz coordinate system defined in terms of Ben. We're taking Ben's world line to be the t-axis. And then we can plot the trajectory of Dan and Al relative to this coordinate system. We're going to make some simplifying assumptions as usual. So we'll suppose that the world line of Dan actually goes through the origin of this Lorentz coordinate system. And we're going to suppose that Dan and Al recede from Ben only along the x-axis and not along the y or z axis. And again, that's just to simplify the calculations. Okay. So let's suppose that in Ben's relative to the coordinate system defined by Ben, Dan is traveling at half the speed of light. So Dan travels 500 light hours distance in 1,000 hours. So he's traveling at half the speed of light. The 1,000 hours is measured by Ben. Okay, so in 1,000 hours as measured by Ben, Dan has travelled along the x-axis by 500 light hours. So we can give an equation for the trajectory of Dan, and given this information we have about the speed at which Dan is traveling according to this frame of reference defined in terms of Ben. And the equation is x, so the x value is just half of the t value. So that corresponds to the assumption that Dan is traveling at half the speed of light, according to Ben. So the speed of light, the light cone, would just be the line x equals t. So light travels at 1 light second per second. The x unit in light seconds would just correspond to the t unit in seconds for every point on the world line of a photon. Okay, so we'll suppose that Al is a clock that's co-moving with Dan, and we'll just suppose that the lines are going to be parallel, but we're supposing that Al is somewhat distant from Dan, right? So the world lines aren't the same, and we'll suppose that Al's trajectory differs from Dan's trajectory just by a certain number of light seconds along the x-axis. So that number is represented by a. And so the trajectory of Al is given by the equation x equals half t plus a, right? So it's the half t that ensures that they're parallel, and the addition of a that just indicates that the trajectory of Al differs from that of Dan by a units along the x-axis. Okay. So, for instance, where t equals 0, then Al just occupies a point that is a units distant from the origin along the x-axis. Okay, so as I've said, the light cone, a light ray emitted from the origin point, is going to traverse the line x equals t, right? So this is a 45-degree line, just representing the fact that obviously light travels at 1 light minute per minute, right? So the fact that it's 45 degrees is, just reflects the fact that we're measuring distance in light minutes. So obviously, light travels at 1 light minute per minute. So the straight blue line represents at least the initial segment of the light trajectory from the origin. So it's 45-degree line. Okay, so we've got an equation for Al's trajectory, and we've got an equation for the light ray, which is just x equals t. Al's trajectory is x equals half t plus a. And so basically, they intersect, right, at point P. So the line describing Al's trajectory intersects with the line describing the trajectory of the light emitted from the origin, intersect at point P. But because we've got equations for each of them, we can calculate the coordinates of P. Specifically, we just substitute. So we take the equation describing Al's trajectory, we substitute in the equation describing the light ray's trajectory to get 3. Just do a bit of rearrangement and simplifying, just basic algebra, and we get a t coordinate for P, point P, namely t equals 2a. And we know that because this point lies on the trajectory traversed by the light, the trajectory described by x equals t, we know that the x value of p is going to be the same as the t value of p. And so the coordinates of p are just 2a, 2a. Okay. So basically the light, so we've got the coordinates for p. Now, when the light reflects off Al, the trajectory of the resulting ray, it has a slope of -1, and an origin at the point 2a, 2a. So again, light's just going to behave the same way. It's going to travel at 45 degrees, and we know where the origin is, and basically the only line with the slope of -1 that passes through 2a, the coordinates 2a, 2a, has this equation. So x equals -t plus 4a. So we can now calculate the coordinates of the point Q, where this reflected light ray reaches Dan, which is the intersection of this light ray, the trajectory of the light ray, with the line giving Dan's trajectory, right, which we said was x equals half t, just reflecting the assumption that Dan's traveling at half the speed of light. Okay, so we just do some basic algebra, and we get t equals 8 over 3a as the t coordinates, and we know, because this is a point on Dan's line, which is described by this equation, we know that this is going to hold true. This equation is going to hold true of the point. So we know that x equals half of t. So this allows us to calculate the x value of the point, given that we've got the t value of the point. And again, just doing some simple algebra gives us this pair of coordinates for the point at which the light reaches Dan. So in other words, for the point Q. Okay, so basically what this allows us to do is allows us to calculate, give a calculation of the distance between Dan and Al, according to Ben's coordinate system. Right, we suppose that 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 Dan shows 180 minutes having elapsed between the light leaving the origin and being reflected back to Dan. So that's just the assumption that that Al is 90 light minutes away from Dan in Dan's coordinate system. So this gives us a measure of the interval along Dan's trajectory. And so we could basically just do some calculations to determine that the point where Al's trajectory intersects with the t equals 0 axis of Ben's coordinate system is where x equals 77. So according to Ben's coordinate system, the two clocks are a constant 77 light minutes away from one another, whereas, as we've seen in the coordinate system of Dan, they're 90 light minutes apart, right? So this gives us the phenomenon of length contraction. So according to Dan, Al and Dan are 90 light minutes apart. According to Ben, according to Ben, yeah, I said it right the first way around. According to Dan, Al and Dan are 90 minutes light minutes apart. According to Ben, Al and Dan are just 77 light minutes apart. So we have length contraction, right? So the distances, if you're measuring the distances between co-moving clocks, then if you're in the reference frame of the co-moving clocks that you're measuring the distances between, then you're going to measure those distances to be the longest that anyone measures them to be. Anyone who's not co-moving with you is going to measure those distances to be shorter. And that's the phenomenon of length contraction. And we've just given a mathematical demonstration of that phenomenon. Now, it turns out that things are symmetric, so that whilst Ben regards Chloe as 90 light minutes away from Ben, relative to Dan's coordinate system, Ben and Chloe are only 77 light minutes apart. So again, whilst Ben reckons the distance between Ben and Chloe is relatively long, Dan reckons it's relatively short. And so again, we have an illustration of the phenomenon of length contraction. So basically, this is all just, sort of a mathematical demonstration of something that we'd already noted, namely that there's this empirically observable phenomenon of length contraction. That is to say that lengths, like the length of the train in the Einstein example, of objects appear longest to those who are in the same reference frame as the objects, right? So the train in the Einstein example seemed longer to Alice than it did to Ben. Sorry, Bob it was, not Ben. I'm getting confused between my B's. Appeared longer than it did to Bob, who was sitting by the side of the track. So because Alice was in the same inertial frame as the train, her measurement of its length was the longest. People in reference frames that are moving inertially relative to the train are going to measure its length to be shorter. And so this is what we see now is just a mathematical demonstration of this fact, right? So an observer who's co-moving with Al and Dan is going to measure them to be 90 light minutes apart, whereas an observer who's not co-moving with them, who's moving at some inertial velocity with respect to them, for instance, an observer on Ben's trajectory, is going to measure the distance between Dan and Al to be less than 90 light minutes. In this case, it was 77 light minutes, thus sort of mathematically demonstrating this phenomenon of length contraction. So take-home message, yeah, as I said, like a lot of maths, but take-home message, length is not, in the sense of distance along the x, y, and z axis, is not something that's invariant across reference frames in Minkowski spacetime. Whereas interval, space-time interval, is something that's invariant across reference frames. So again, we have the sort of, I guess, unless one wanted to take reality to be somehow reference frame relative. A natural thing to say is that what's physically real or physically significant are things that are invariant across reference frames, and interval is invariant across reference frames in Minkowski's space-time. So you might say we have a notion of absolute interval, even though we don't have a notion of absolute spatial distance. Okay, so that's plenty for now. Thank you for bearing with me through what's quite difficult material, and we will. Well, I'll speak to you all again next week. Thank you. Bye.